Black holes, perhaps the most mysterious and extreme objects in the cosmos, are divided into three main categories by mass: stellar mass, supermassive, and intermediate mass, although scientists still argue about the exact boundaries that differentiate between these classes. A hypothetical fourth class, primordial black holes, believed to have existed during the early days of the universe, is still elusive, with their existence still unproven. These celestial events, while varied in size and cause, have the common characteristic of gravitational pull so strong that not even light can escape it. Their observation not only defies our concept of physics, but also provides insights into the history of galaxies, the structure of space-time, and the early universe's conditions. Every type of black hole has a special tale to share, ranging from the supernova deaths of giant stars to the enigmatic seeds of galaxy giants and the hypothetical leftovers of the universe's beginning. Number 1. Stellar mass black holes, the lightest and most widespread type, are created in the hot remains of the deaths of enormous stars. When a star with more than 8 times the mass of the Sun runs out of nuclear fuel, its core collapses catastrophically. The outer layers bounce back in a supernova explosion, dispersing elements such as iron, gold, and uranium into space. And the destiny of the core depends on the initial mass of the star. If the initial mass of the progenitor star is close to the limit, about 20 solar masses or higher, the core will collapse into a black hole. These objects are generally a few to hundreds of solar masses, though they grow as time passes due to accreting gas, dust, and even other black holes via collision. The existence of stellar mass black holes is largely discovered through their interaction with companion stars. In X-ray binary systems, for example, the gravitational force of a black hole removes material from its stellar companion, directing it into an accretion disk. As this disk moves inward, friction heats it to millions of degrees, producing X-rays that can be detected by telescopes such as NASA's Chandra X-ray Observatory. About 50 such systems have been found in the Milky Way, with well-known examples being Cygnus X1, the first black hole to be confirmed, and V404 Cygni, which is famous for its spectacular outbursts. But these observable systems are a tiny percentage of the estimated 100 million stellar mass black holes hiding in our own galaxy alone, the majority of which wander unseen in the shadows. The binaries form from incompatible pairs of massive stars. The more massive star ages more quickly, losing its outer layers in stellar winds or outbursts before it collapses into a black hole. Over time, the black hole may siphon material from its companion, a process that can alter the system's dynamics and eventually lead to mergers. The advent of gravitational wave astronomy has revolutionized the study of such events. Observatories like LIGO and Virgo have detected ripples in space-time from merging black holes, some of which defy expectations. For instance, the GW 190521 event was comprised of 2 black holes with masses of 85 and 66 solar masses, a combination that defies conventional stellar evolution models, since stars of this mass are believed to be destroyed by parent stability supernova. Such findings suggest complicated routes to black hole formation, such as hierarchical mergers in dense stellar environments such as globular clusters. Number 2. Supermassive black holes. At the other mass extreme are supermassive black holes, SMBHs, gargantuan objects at the centers of almost all giant galaxies, varying in mass from hundreds of thousands to tens of billions of solar masses. These giants dominate their parent galaxies through gravity and energetic explosions. The Milky Way's own SMBH, Sagittarius A, tips the scales at a paltry 4 million solar masses. But Home 15A's black hole is the record holder, at 40 billion solar masses, a whopping 10,000 times heavier than Sagittarius A. SMBHs are still cosmology's biggest mystery. Observations of quasars, extremely luminous active galactic nuclei powered by SMBHs, reveal that such objects existed less than 1 billion years after the Big Bang. This presents a chicken or egg dilemma. How could black holes grow so massive so quickly? One theory posits the direct collapse of primordial gas clouds into seed black holes, tens of thousands of solar masses in size. bypassing the stellar phase entirely. Otherwise, early supermassive stars, 100,000 solar mass objects, could have collapsed into large black holes that subsequently grew exponentially by accretion and mergers. SMBHs accrete gas, stars, and small black holes to grow, building luminosities equal to or greater than entire galaxies. In active phases, relativistic jets explode from their poles, fueled by magnetic fields and rotating erga regions, affecting star formation over vast distances. The Event Horizon Telescope's now famous photo of M87 shadow in 2019 offered direct visual proof of an SMBH's event horizon, while current research on Sagittarius A follows stars such as S2 orbiting it at velocities of more than 15 million miles per hour, providing accurate measurements of its mass. Galactic mergers are central to SMBH evolution. When galaxies collide, the central black holes spiral toward one another, merging ultimately in a burst of gravitational waves. Such events, observable by future observatories such as LISA, may account for the presence of binary SMBHs and ultramassive black holes. Theoretical final parsec problem, dealing with difficulties in modeling how black holes lose enough energy to merge within the universe's age, however, is still an open question. Number 3. Intermediate mass. Black holes. The black hole mass gap between stellar mass and supermassive black holes has long been a puzzle for astronomers. Intermediate mass black holes, IMBHs, theoretically between 100 and 100,000 solar masses, are supposed to be created by successive mergers in high-density star clusters or through the collapse of large population 3 stars in the early universe. Although theoretically ubiquitous, definitive proof of IMBHs is still sparse, giving them the nickname missing link black holes. Possible IMBH candidates are ultraluminous X-ray sources, ULXs, which have X-ray emissions at rates indicative of accretion onto a body too massive to be a neutron star. An example is HLX, one in galaxy ESO 243-49, which has a mass of approximately 20,000 suns and is a prime candidate. Gravitational wave signals, like GW190521a, merger resulting in a 142 solar mass remnant, also point toward IMBHs, though this interpretation is still controversial. Globular clusters, which are old star groups, are IMBH's best hunting grounds. Observations of the Omega Centauri cluster show stars moving around a hidden central mass of 40,000 solar masses, and comparable motion in the Andromeda Galaxy's cluster G1 indicates an IMBH, or tidal disruption events, when a star is torn apart by a black hole's gravity leave temporary signatures. Such events as Assassin 15LH, which emitted energy equivalent to 100 supernovas, can be indicative of IMBHs, although other explanations are possible. Number 4. Primordial black holes. Primordial black holes, PBHs, are a theoretical class formed not through stellar collapse, but through density fluctuations in the hot, dense plasma of the early universe. Introduced by Stephen Hawking in 1971, PBHs may have been created during the first second following the Big Bang, when regions of high density, due to phase transitions or cosmic inflation, collapse straight into black holes. Their masses can range from an incredible scale, subatomic masses, micro black holes, to thousands of solar masses. PBHs are of special cosmological importance. PBHs with masses close to asteroids might account for dark matter, the unseen matter that dominates normal matter by 5 to 1. Nevertheless, limits from microlensing surveys, example, OGLE, and the cosmic microwave background, CMB, have practically eliminated PBHs as the main dark matter component. Interestingly, PBHs at the asteroid mass window, approximately 10 to the power of 17 grams, are still tenable, since evaporation through Hawking radiation would produce gamma rays, not yet observed. More massive PBHs at stellar intermediate masses may be seeds for SMBHs or account for unusual gravitational wave events. The LIGO-Virgo observation of merging black holes with nearly solar metallicities. For example, has fueled the speculation that certain events are due to primordial, not stellar remnant, black holes. Hawking radiation, a quantum mechanical phenomenon, where black holes shed mass, mandates that lower mass PBHs evaporate more rapidly. A mountain-mass black hole, 10 to the power of 12 kg, would be gone in an explosion of gamma rays after 10⁻⁹ years, while Earth-mass PBHs would last 10⁻⁵ years. Search efforts target transient signals such as gamma-ray bursts, stellar microlensing, or CMB distortions from PBH accretion. Black hole research is at the vanguard of astrophysics, where general relativity, quantum mechanics, and cosmology intersect. Future instruments hold out the promise of revolutionary understanding. The James Webb Space Telescope, JWST, will investigate SMBH growth in the early universe. The Square Kilometer Array, SK, will chart galactic centers with unprecedented resolution, and space-based gravitational wave observatories will probe the cosmic symphony of black hole mergers on all mass scales. That's it for today. If you have any ideas for our next video, let us know in the comments below. Don't forget to like, share, and subscribe for more fun videos. Thanks for watching.